In chapter 23, it's all about the energy associated with electrical interactions. And we're going to be using concepts from chapters 6 and 7 back in Physics 1, the work done by a force, the change in potential energy of an object, conservative forces, okay? All those concepts we're going to bring back and look at them under the new scenario of a charge in a field versus a object in a gravitational field. So when a charged particle moves in an electric field, right, the field exerts a force on the particle. And that force is given by F equals QE. So that language, right, the field exerts a force, it's an important sentence. The way that we have been talking about force is we were always talking about charges exerting forces on one another, but we're kind of changing the language now. And what we're saying is that if this is the charge in question, our test charge, we're looking at, wrong direction. We're looking at the force that this positive charge, our test charge, feels when it's in the electric field of the negative charge. So, I mean, we're kind of still talking about two charges, but really we're changing the subject, right? The positive charge is now in the field created by the negative charge, okay? It still feels a force due to the negative charge, but now we're discussing that force in terms of a test charge and a field. And so that field, well, it can be produced by a single charge, and it could also be produced by lines of charge or plates of charge or any kind of object that possesses a net charge. And so in this situation, we use two plates of opposite charges, and we're going to give that a name in the next chapter. It's actually called a capacitor in chapter 24, but for now it's just two plates, opposite charge separated by some distance, kind of like a dipole, kind of, right? And what happens is this arrangement creates a very nice and uniform electric field, and that electric field is going to be responsible for exerting the force on our little test charge. Okay, so that's the new way to look at this picture. And so what we're going to talk about is the fact that the field, E, is going to do work on the particle. And we're going to talk about the fact that this force is a conservative force. And the fact that it's conservative force means that we can express the work in terms of electric potential energy, right? So these are all concepts that we've already learned about in the scenario of objects in a gravitational field, objects with mass. Now we're going to be talking about particles in an electric field with charge. So let's take another, look at this. I kind of already explained it in the previous slide, right? So we have these charged metal plates, opposite charges, creating that nice uniform electric field. And we put a positively charged particle in that field. What's going to happen? It's going to feel the force. It's going to feel the force, and the direction and magnitude of that force is going to be given by this equation, F equals QE. And so there's a couple different ways on how you can determine what direction that force is going to be. I think the easiest way is that you imagine what's creating that electric field. And in this case, you don't have to imagine because the plates are there, but maybe in another problem, the plates wouldn't be there, and you would just see an electric field vector. So you imagine what's creating this electric field. Well, electric fields always point from positive to negative, right? Positive to negative. So if this positive charge is in this electric field, it's going to be drawn towards the negatively charged plate, creating the field. In other words, a positive charge will always move down the electric field, okay, in the direction of that vector representing the electric field. It's going to move parallel, right? And we see that with this equation right here. has to be in the same direction as E when Q is positive, okay? So the field exerts a downward force on the positive test charge, and I'm going to spare you all the, mathematical proofs and all the experiments that show, and I'm just going to tell you straight away that these experiments and all these proofs show that the work done on the charges by the field is independent of the path taken, okay? Just like mass and gravity. So what does that mean? Does that phrase kind of sound familiar? Independent of the path taken, right? That means that the force responsible for that motion is a conservative force. So we've established that this force, F equals QE, is a conservative force. In the same way that, F equals mg, right? That was also a conservative force. And so that allows us to make some generalizations about the work done and relating it to, right, the work done and relating it to the change in potential energy. So, right, work done by conservative force is the change, well, it's actually the negative change in potential energy. You may remember that little detail. So if we define delta U, right, anything with a delta is always final minus initial. For example, B minus A, right? If B is our final point, A is our initial point, so it's going to be B minus A. Well, that negative sign just tells us that the work done is equal to A minus B, okay? What A minus B? What? The potential energy at A minus the potential energy at B, right? This is all from, this is also I should have wrote the equation. Now, maybe equation 7.2 in the earlier chapters from Physics 1, right? This is the exact same equation that we did last year. But we were talking about a mass in a gravitational field, okay? So, so recall this fact, right? Work done by conservative force means that we can relate it to a change or a negative change in potential energy. And then the work energy theorem, which follows the work done by conservative force, that allows us to relate the change in kinetic energy to the change in potential energy. And further, right, where that comes from is the fact that the total energy, oops, sorry, that should be a U, not a K. The total change in energy of the system is 0, right? That's another condition of a conservative force. So, and the work energy theorem, another statement of those two, right? And that's where this comes from. So we have all these relationships now that we can use to help us solve problems without having to do crazy integrals, right? Or deal with crazy vectors. In the same way that in Physics 1, we were busy adding up free body diagrams and adding up the forces and directions. And then we got to chapter 6 and 7, where we kind of dealt with everything as a scalar, everything in terms of energy. And the math became a lot easier, and we were able to answer the same types of questions. So that's kind of what we're going to do here with charges and electric fields. So I mentioned already a few times, right? The analogy that of a mass and gravity to Physics 2 is a particle in an electric field. And so swapping the weight vector, right, with the force, F equals QE, and the weight was mg, right, where g was a vector and E was a vector, and M and Q were scalars, right? You can see the one-to-one correspondence there. So if you had success in understanding potential energy changes in the situation with mass and gravity, then feel free to refer to that in order to answer questions about particles and fields, okay? If that wasn't too fuzzy, then, I would stick to working on this physical picture and understanding how work, potential energy, force are all related in the context of a charge in an electric field. So we're going to kind of do like a mini proof, okay? Just as a way of introducing what the potential of a charge in the vicinity of another charge is. What is that potential energy, right? I didn't give you the value. All I told you was that the force is conservative and therefore the work done is equal to the negative change in potential. So we're going to show in the case, let me draw a picture of what's going on here, right? We're gonna kind of determine what the electrical potential energy is of 2-point charges using this general statement for the work done. Okay, so we've talked about the work done. So let's do this. So let's say we have a particle, charged particle, and he has value of charge Q naught, and he's in the vicinity of some other charge, okay, Q. Doesn't have to be bigger or smaller, but just to kind of show who's the test charge and who's the charge that is supplying the electric field. Okay, so since Q, we're just going to deal with both of them being positive. The electric field vectors we know point away from positive charges, right? And so this charge is going to move around, right? He's going to feel a force due to that electric field. And that force, we can use the definition of work done by a force, right, to calculate the work done and see if we can come up with an equation for that matches the fact that this is a conservative force, right? And we're going to try to work towards minus delta U. We're going to start with the definition of force for any type of force. I mean, the definition of work for any type of force. And we're going to see if we can turn that into negative delta U. So right from chapter 6, we learned that the work done by a non-uniform force, right, in a direction of its displacement is F dx. So we are moving basically this charge from one location, let's say, to another location, okay, in this direction. The direction is arbitrary here. And so the force that this test charge Q naught feels is given by Coulomb's law, which we know. And so what we can do is we can plug Coulomb's law into the force, into the work done by the force. And if we kind of switch around our variables, and instead of talking about X, we're going to talk about R, right? Because this is the R direction away from, from source to field point, right? So the E field is all in the R direction. And the movement of charged particle Q naught is also going to be in the R direction. So we're going to switch to R variables, plug in our Coulomb's law, and then our integration variable is going to be dr. Okay, so now we're tasked with integrating this function, which is quite simple. Let's move all of the constants out. And all we're integrating is 1 over r squared dr. And that just happens to be negative 1 over r evaluated from RA to RB, right? That's the integral of 1 over r squared is negative 1 over r. So we plug that in and we turn that integral out. And I kind of, I wrote the answer here, but it's all distributed strangely. I don't know what I was thinking there. I want to write it so it becomes more clear how it turns into this equation. Right, so we had negative 1 over r from RA to RB. So I'm going to, and I have my Q's here, right? And so that's going to be negative 1 over RB minus a negative 1 over RA. And when we kind of simplify that expression there, we get Q naught over 4 pi epsilon naught, right? Swapping these around, 1 over RA minus 1 over RB. Okay, which is that right there. And so, well, we know, I already convinced you that the work done by a electric force is a conservative, which is a conservative force, is equal to, right, negative delta U. So this expression must be equal to negative delta U. And if negative delta U is U, right, the potential energy at point A minus the potential energy at point B, then this term must be the potential energy at point A, and this term must be the potential energy at point B, which in general states that the potential at any place R is any kind of distance between two charges R is 1 over 4 pi epsilon naught Q naught over R. Okay, so what we kind of just, had some fun doing some integrals, and we sort of derived the expression for an electric potential energy between two charges. All right, and it looks awfully similar to other expressions that we have learned so far, like force, it's only off by a factor of 1 over R. Electric field, it's off by a factor of Q and 1 over R, right? And they all have very similar forms. So this is the expression for the electric potential energy of 2-point charges. So in this example, we're not going to do it together in this lecture, but I am going to upload all of my work for this example. It's a really good one to get you kind of warmed back up with the ideas of total energy is 0, force is conserved, delta K equals delta U, applying all those expressions that we learned back in chapter 6 and 7 to this new scenario of a force on a charged particle due to an electric field. So the electrical potential energy we defined between 2-point charges. What about if there were several point charges? The way that you would find the total potential energy of this system is you would simply add up the potential energy between your particle that you are interested in and all of the other ones in the system, okay? So the potential energy associated with that particle Q naught that you want to know, right, it's going to depend on the distances between it and the other charges. And so we already know this about energy, right? Energy is one of those things that you can just add up. So we're just going to be adding up basically the previous equation. If I go back, right, we're going to just be adding up this equation a whole bunch of times for all the pairs, right? So the pairs would be Q naught with 1, Q naught with 2, and Q naught with 3. All right, and in summation notation, it looks like this. So not too crazy, right? Let's do this example together, and let's kind of put that idea to the test. So we have 2-point charges. This picture is kind of the picture for part B. So the picture for part A is we have 2-point charges, just these two. And let me just go ahead and write all the details down. We have these 2-point charges on the x-axis, okay, right, of charge negative E and charge plus E. Find the work done by an external force, okay, that word's going to be important, by an external force to bring a 3rd-point charge, Q3, from infinity, so from infinity, let's put infinity over here to the right, all right, to x equals 2A. All right, so we need to find the work done or the work required to physically move Q3 from infinity, where it doesn't feel any of the other 2-point charges, to x equals 2a, where it's going to start to feel the effects of the other 2-point charges. Okay? And then part B is, here's that final arrangement. What's the total potential energy? So let's go to the example. I guess I should have drawn the picture here, shouldn't I? I think oops. I was using touch earlier because I forgot there we go. Don't need to do touch anymore. So I highlighted an important word in the previous slide. It was external force. Okay. The work done by an external force is opposite in sign to the work done by the force, the electric force. Okay, so external force is equal to negative of the work done by the electric force. In the same way that the external force, right, the work that it requires me to, right, a person or somebody to move a ball against gravity or with gravity, right? That's going to be the opposite sign as the work done by gravity. Okay? So you can use the, ball and gravity analogy to help you kind of better understand that. Well, let me just go ahead and express it in terms of the charge and the electric field. Or maybe, how about in the situation of two charges, right? So if I have a positive charge and then I'm bringing in another positive charge, and I'm applying the force required to bring them really close together, because they don't want to be together, right? So it's taking me an external force, energy. It's costing me energy to push those two together. Kind of like, right, it costs, like if you have the two sides of a magnet, the two positive sides of a magnet, and you try to, like if you ever played with bar magnets before and you try to squeeze them together and you can feel the resistance, right? You can push as hard as you can and they can't get together, right? You're putting energy in. So the work you do is going to be positive, right? So in this case now, we're talking about external work, which would be opposite in sign to the work done by an electric field, okay? And so remember the work done by an electric field. We said that because the Coulomb force is conservative, it's equal to negative delta U. So that should mean that the work done by the external force, you and me or whoever, should be equal to just delta U. And so what we need to do is we're going to need to figure out what's the change in potential energy that this third charge Q3 experiences when it is brought from infinity, where it doesn't feel anything, right? If he's infinitely far away from Q1 and Q2, he has no idea that they're even there. He feels no force from them, to a place really close to Q1 and Q2. So the first thing we're going to do is, well, what is the total energy, potential energy of Q3 when it's at position infinity? Okay, so we can kind of just say it's 0 because he's not feeling the force. But if you're not so sure about that, we can go to the equation, right? So this is going to be Q3, and we're going to do Q2 over the distance between Q2 and Q3, right? And then the second term, well, what's the energy between Q3 and Q1 at a distance R13? All right, so what would those distances be if we are at infinity? Well, they would be infinity, right? And we know that 1 over infinity is 0. So that would make these 0, right? And so the total potential energy when Q3 is at infinity is 0. Well, what about the potential when he is at location x equals 2a. Okay, let's do the same procedure. Let's add up the two terms. Q2, Q3 over R23. Q1, Q3 over R13. So what are those distances? And let's plug in also the values for Q. Q2 was minus E, no, Q2 was plus E, Q3 was plus E, so that gives me E squared. The distance between 2 and 3 is simply A. Q1 was negative E, Q3 is, oops, I should not have written parentheses, right? That would ruin my negative sign. It's a negative E squared, right? It's negative E times E. And the distance between Q1 and Q3 is 2A. So now I can, add these together, clean it up a little bit, create some common denominators here. I can multiply this by 2 over 2. And so then I get 1 over 4 pi epsilon naught 2e squared minus e squared all over 2a. And that leaves me with e squared over 2a. And so is that my final answer? Well, what is my final answer? It's the work done by the external field, which is equal to delta U, which is equal to final position minus initial position, right? Because there's no negative sign. So my final position is U at x equals 2a. My initial position is U at infinity, right? That's the work done by the external force. And so then it's basically going to be just this guy, right? Because this is 0. And that is 1 over 4 pi epsilon naught e squared over 2a. And so then the work done by the external force is simply this. Okay? So it's kind of almost like a trick question, right? You have to be really paying attention because it was asking for the work done by the external force. So now what if this question asked what the work done by the electric force would be? Okay, well, it would just be this in opposite sign, right? Because all you would do is reverse your final and initial positions, okay? So in part B, so we have this arrangement, 3 charges kind of in a row, right? Separated by distance A. What's the total potential energy of that system of 3 charges? So we're going to be adding up the pairs, right? The energy pairs that each of them feel from one another. So we have what 1 feels in the presence of 2, and we have what 1 feels in the presence of 3. We have what 2 feels in the presence of 3. And are there any more unique pairs after 3? No, right? Or else I would say 3 to 1, which we already have 1 to 3. We have 2 to 1 as 1 to 2, right? We don't want to repeat these pairs because we would be doubling the energy, right? Because the energy is associated with each pair in vicinity to one another as if the other one isn't there. So we're not going to be counting it twice. So we have 3 terms for the total energy. We're going to have 3 terms. We're going to have Q1 and Q2. We're going to have Q1 and Q3. And then we're going to have Q2 and Q3. Okay, no repeats. If you do want to repeat it, you just have to divide your answer by 2. Okay, but just don't repeat it. So, right, find all the unique pairs. So now it's just a matter of plugging everything in. All right, Q1 and Q2, negative and positive, distance of A. So we're going to get a negative E squared. 1 and 3, negative and positive, distance of 2A. So we're going to get another negative here. And then finally 2 and 3, positive and positive over a distance of a. So we get positive e squared over a. So we'll have a little bit of cleanup here to do. Let's multiply this guy by 2 over 2, multiply this guy by 2 over 2. And we'll get negative 2e squared minus e squared plus 2e squared. Well, I guess I didn't need to do that, did I? I could have just seen that these cancel, but oh well, we're going to practice our common denominator techniques. So that just leaves us with negative e squared over 2a. Okay, so that's the total energy of the system. So, find the total potential energy. So, okay, so right, so that's example 23.2. And so we're kind of dealing with, I know in the earlier slides I said we're going to change the conversation and we're going to talk about charge in terms of electric field, but here we are doing calculations of, finite charges. So what I'll say to that is, be prepared to flip back and forth, right, between those two notions. The notion of force being between two particles and the notion of force being between a charge and an electric field. Okay, so be prepared to flip between those two ideas in whatever way is going to help you solve the problem better. And obviously in this way, it makes a lot more sense to solve the problem using the discrete charges. So let's do kind of a conceptual check here. So here we have 3 positively charged point charges, charge point charges. Yeah, okay, sounded weird. Arranged in kind of like a triangle. What is the sign of the total potential energy of this system? Is it positive, is it negative, or is it 0? So right in the other example, we saw that the sign of the charge basically determined the sign of, the sign of each charge, determine the sign of that term. So here we have all positive charges, so we don't have anything that's going to introduce a negative sign. And so the total potential energy of the system should be positive. What about the sign of the total work you would have to do, okay, aka external work, not work by the field, you would have to do in order to move these charges infinitely far apart. Okay, so let me give you maybe an analogy that will help you understand this, right? How easy would it be for me to try to separate those 3 charges? I would say it would be pretty darn easy because they don't want to be close to each other, right? They are all the same sign. They want to spring apart as fast as possible. So it would cost me negative work, right? It would do the work for me to spring them apart, right? So therefore the work by an external force or the work by a person to move those positive charged particles apart, well, it's going to be negative because they already want to fly apart, right? The force due to the electric field is going to push them apart for me. So external work would be negative. All right, it'd be negative external work. It's going to do the work for me. So that's one way to think about it. And so if one of those spots was changed to a negative sign, okay, then you would have to do a little bit of calculations. In this case, they're all equidistant from each other, so, right, I could just say actually they're all R, but R1, R2, R3, they all equal each other, right, because it's on an equilateral triangle. So if one of these charges was negative, you would be adding your potential, right? Negative times a positive would be a negative term. Negative times a positive would be a negative term. and the work done would be negative of that, right, by an external force, and the work that you would have to do would be positive, right, because they would be attracted to each other. So I would have to like overcome that attractive force with some energy. And so the work then, if one of the charges was negative, the external work would be positive, right? Because they want to be together. So if I want to pull negative charge away, I'm going to have to really work hard at it because they have that Coulomb force of attraction. Okay? So let's bring up a final, I don't know if it's going to be the final, but let's bring up another term, and it's basically just a scaling down of electric potential energy. So we're going to call it electric potential, right? We're dropping off the energy because it's an electric potential energy per unit charge. And we call this potential letter V, okay, with units of volts, which you probably have heard a lot about volts in your life already, right? Charging your devices and charging your car. So a volt is simply electric potential energy scaled by charge, okay? And so you can rearrange that to show that your electric potential energy is simply your test charge times potential, okay? Whatever this potential is that we're going to define. So what is this potential? Where does it come from? Well, if we scale the work done to move that test charge from point A to point B, right? We're going to divide everything on the right-hand side of that equation by Q naught. And if we divide the delta U by Q naught, what we're left with is that change in potential. So change in potential is directly related to change in potential energy. Okay, it's just another way to think of potential energy, but it's scaled by charge. In the same way that force, right, we expressed as QE, but we also define the electric field as F over Q, right? The force scaled by our little test charge Q naught. So we're treating energy in the same way, right? If force scaled by Q is electric field, then potential energy scaled by Q is potential. So, so how we define, let's just quick look at this definition, right? So negative VB minus VA is simply, right, VA minus VB. So what we call VA minus VB is the potential of A with respect to B, okay? That's VA minus VB. That's the definition, okay? So you may see in your homework some expressions of potential with respect to another position, and so that ends up being VA minus VB, not VB minus VA. So we can calculate electric potential in the same way that we were able to calculate the electric field, right? Except now the denominator of that expression is simply R and not R squared. Okay, so these equations are going to mirror the equations that we use to calculate an electric field of an object, okay? But the difference is the denominator is a factor of R and not R squared. So we can calculate the electric potential of, a single point charge, a system of point charges, or a continuous charge distribution. And the techniques that we use to integrate a charge distribution are going to be exactly the same as in chapter 21, the end. Okay, all those integration techniques are going to be the same. We may just end up with a slightly different integrand, but you will still use the table. You'll still convert dq into, for a line charge, right, lambda dx, right? You're still going to do those conversions, but your resulting integral might be just slightly different, and therefore you use the integral table to get the correct answer for the integral. So I'm going to pause here.